Hello everyone, welcome to week 11. This week we're going to be looking at unrealistic shading. So we're going to be doing Toon shading, which is going to comprise of cell shading as well as edge detection using the Sobel filter. So let's start with the Sobel filter first. Both of these parts of Toon shading can be accomplished individually, so we'll just focus on one at a time. Right before we get started though, I want to show you that I have made a change to the scene. Just a minor one. I've added a sphere, a large sphere off to the side of the shack in order for us to get a better idea of how the directional light would hit a curved object, because everything we have here is pretty, well, it's made out of planks. So especially with Toon shading, when we're going to have stepwise cell shading, it's going to be useful to have that sphere there, as you'll see later. Of course, that's a trivial change to the scene that you can add in yourself, but if you don't have it, that's okay. So let's start by adding a new frame buffer. So this one we can put just anywhere. Frame buffer. And it's going to hold our edges. This is essentially going to hold the result of the Sobel filter, and we can call it the edge map. In order to write to that, we're going to need a shader, of course, so let's get our Sobel filter ready as a shader program. We can call it Sobel pass, Sobel filter, whatever you like. I'm actually going to move it up with the other passes so that, it has pass at the end, so why not? That's all we're going to need in terms of new parameters here, in terms of new data members. Let's go set up the frame buffer, and then we'll start getting to this shader. So in game.cpp, I'm going to need to go to the very top in order to initialize my buffer. So let's add one in here. Edge map. It's going to have one color texture in it, simply holding the edges. Nothing more fancy than that. Let's go down to where we initialize our buffers. Cheap buffers. I'll put it after the shadow map. I'm gonna copy paste, make my life a little bit easier. Rename this to edge map, as well as this guy. We're not going to be initting a depth texture though, not on this guy. It's kind of like a work buffer. It's not going to need depth. We're not really going to be rendering geometry to it. So I'm going to copy one of these lines that inits color. I guess I'll copy from here. So our edge map is just going to have a color texture. It's going to be different than the ones we've used before though. If you think about what we need this buffer to do, all we really want is more or less a Boolean value representing is there a texture at a given pixel. We don't really need the complexity of RGBA. So what we can actually do to save on memory is we can use not just RGB, but we can go all the way down to one channel, a red channel. And the texture will simply have one channel, right? You can only write to that one channel, so instead of writing a vector color to it, when we write to this, it would simply be sending one float out of the fragment shader. A lot of AAA games will have textures like these that behave in this way, and we've been using one already, the depth texture, the one that's created and used for us by OpenGL. That one's a single channel texture as well, representing simply how far away in a magnitude was the nearest piece of geometry from a given pixel. So with that out of the way, I want to start the shader now that we know what kind of format we're going to be writing to. So let's go to our assets, shaders. Let's make a new folder, call it Toon. In there, I'm going to create a new text file. I can call it sobel.frag. Now that we have that, let's add a similar folder, new filter in Visual Studio. Call it Toon. Then we can add an existing item, assets, shaders, Toon, Sobel. So let's open that guy up. Of course, we're going to start with version 420. Now, what are we going to be doing here? So our main function is going to need to compute some sort of edge factor. And that edge factor is going to be a single floating point value, as we saw from the frame buffer. So instead of having an vec4 out color, we can have a simple float, and of course we can call it whatever we want, so I'll say out edge. Now remember from in class, we were talking about what buffers the Sobel filter should be applied to, and in fact we're going to be applying it to two. So the first one going to be coming in as a texture. Well, both of them will be, but the first one will be uniform sampler 2D, so we could read from it U normal map. And then another sampler 2D to read from the sorry, not the position map. I should call it the depth map. Other than that, just like when we had our Gaussian blur for bloom, if I open up one of the blur shaders, remember we had this pixel size that told us, well, the width of a pixel in normalized space, right? Because one side of the screen is 0 while the other side is 1. So the width of a pixel is actually 1 over the size of the screen. And the shader needs to know that in order to be able to move across properly to sample from neighboring pixels. And that's not going to be any different in the Sobel filter. We're going to be sampling a kernel, an area of pixels, so we need to be able to translate over and up exactly the amount we need to hit those pixels dead on. So not only are we going to need a pixel size, but we're going to need a pixel size for both dimensions. One for the x-axis and one for the y-axis. And so we can just put them under the same name by making this a vec2. X is going to be 1 over width of the screen. Y can be 1 over the height of the screen. And we'll be able to translate and perform the kernel properly. And of course, this is going to be applied as a post-processing effect, so there's going to be a full screen quad. In order to be able to sample all these textures properly, we're going to be reading from the texture coordinate in order to get all the respective pixels and data at one location. So some edge factor will be computed, of course, but I'd like to set this up using functions. We haven't done that before, and I feel like this shader looks really neat if you use functions, so let's do that. So let's create 4 functions. Let's create a normal horizontal. We'll fill in the parameters later. Essentially, now a vertical one. And then the same for the depth. In fact, I can just copy this. So that we have a function that returns a factor representing the intensity of an edge there, or whether or not an edge existed, for both horizontal and vertical on both the normal map and the depth map. Let's fill in the parameters here. So the normal horizontal Sobel filter needs to know what sampler we're going to be reading from. Right, coding this as a function, assuming that we can give it parameters and it can take them and use them inside. And of course we can tell it what texture coordinate to start from. Let's open these functions up too. Now all of them are going to have the same parameter list, but of course we're going to be supplying something different when we call them. Let's space these out a little bit. So let's start on the first one, right? The Sobel normal horizontal. What we're going to do is we're going to sample on the left-hand side and the right-hand side of this pixel in order to find which pixels have contrast. So if we go into the filter image really quick, where is it? From the PowerPoint. This is our outline for our kernel, right? So the X filter The horizontal filter will detect contrast across the horizontal axis. So we want to sample on these 3 pixels and these 3 pixels. So we're going to have 6 texture reads. We're going to be accumulating them, adding them up in order to determine a final factor representing the contrast. So let's create a sum variable equal to a zeroed vector. If you supply just one value in here, it'll apply to the entire vector, initializing it to 0 really quick. And now let's start accumulating this sum. So first, let's read from, let's say, the left-hand side. So the texture coming in, I don't have to worry about these two. I'm going to be taking this sampler that was passed into the function. So I'm going to take the text map. Now, I'm going to have to offset a little bit here. So I'm going to take the texture coordinate x component, and I'm going to process it differently than the y coordinate. So the texture coordinate x, if let's start with the top left and we'll move down. So we want to go 1 to the left and 1 unit up. So we're going to minus 1 pixel size dot x on the x-axis, and then we're going to add 1 pixel size dot y for the y-axis, and that'll move us up. Now that's going to use, I'm going to specify the type of the texture at the end. That's going to be RGB, right? We're reading from a normal map, so we're going to have 3 values here. I can copy this line 2 more times, and additionally, I'm going to label this as the left column. And of course, afterwards, we're going to read from the right-hand column. Since the values in the middle are 0, naturally, we don't even have to waste our time reading them. So let's change up these second 2 lines to work right. So if we move 1 down, we're no longer going to have an offset on the y. So I can take away that one. However, something's different here. We're going to have a factor of 2. So I'm going to multiply by 2.0. The last one is going to have negative pixel y offset as we move below. So I can copy this block and I can move it to represent the next column, and everything stays the same except we change the x offsets to positive in order to move to the right. Something does have to change here though. Notice that one side is negative while one side is positive. So we could multiply one of these columns by -1. Doesn't really matter which one it is. It works if it's mirrored, all the same. To be consistent, let's say our left-hand column is going to be negative. We can apply that even simpler than a multiplication by just changing these to minus equals, right? If we would be adding a negative value, then it would just be like subtracting it anyway, so we might as well just change the operator. So we've gotten all our sum. It's all been added up together, right? If there were equal magnitudes on each side, it would evaluate to 0. Otherwise, it would be some sort of other value. So how are we going to actually compute that? Well, we have a vector 3, and we want to somehow evaluate this to one single floating point value, right? Essentially, this sum should converge to 0, 0, 0 if there's no contrast. In other words, the length of sum should be equal to 0. So we could have a float edge factor is equal to length of sum, Now, we can actually do this a little simpler too, but the idea is exactly the same. Think about what a length is. The length of the vector is x times x plus y times y plus z times z, the square root of all of that. That square root doesn't really help us here. And generally speaking, if you're working on AAA projects, performance is going to matter, and square roots are something that you want to avoid inside of shaders. So we can get the length of a vector but not have the square root. That would be like having just x times x plus y times y plus z times z. We just have the insides of the brackets. So I might as well write this out. So we have the square root of, right, this shouldn't be news to you guys or gals. If we have this equation here, then that's the length of the vector. So what happens if we have the square root removed? We're left with this. If you take a look at mathematically what this represents, it represents the vector dot product with itself. So I could write that as dot of sum versus sum. This is also equal to the length of sum to the power of 2, right? Canceling out the square vector, the square root. So if you ever want to have the squared length of a vector, you can do it more efficiently by just avoiding the square root to begin with and having a dot product of the vector versus itself. Although it isn't exactly its length, it is still a factor that is representative of its length. It gets bigger as the vector gets bigger. So we can still use it in a case that we don't need its exact Euclidean length. So we're going to take this factor and we're going to return something based on it. So we're going to say if the edge factor is less than 0.7, that can be our threshold that I arbitrarily decided on, that I know works well. If our edge factor is less than this, right? So if the length of the of this vector was less than 0.7, then let's say, you know what, there's no edge. So if there's no edge, what we can do is we can return 1.0. Now let me get to that for a sec. So it might seem counterintuitive that we're returning 1 when there's actually no edge, when we don't want an edge to occur. But here's the idea. We're going to be using this factor to multiply by the color in the scene. So if we multiply by 1, the scene will remain unchanged. However, if we multiply by 0, then we're going to be changing whatever color was there to black. So we'll get black edges. So the reason, again, that we're returning 1 is because multiplying by 1 will actually have no change to the color in the scene. And that actually is all we need to do for our horizontal Sobel filter. Let's go for our vertical one. It's going to be much of the same. Going to have a sum. It's going to accumulate some stuff. Of course, we're going to move over a lot of these offsets to the x-axis. So if we go to our y filter, let's do the top first. Start at the top left and go to the right. So the first one's going to be -1 on the x and then positive on the y. So we're going to have negative on the x, positive on the y. Cool, that one's already set up. Let's do this one. That's going to be simply up 1 and no transformation on the x. So I'll get rid of that guy. And I'll add you pixel size dot y. I want to make sure I have that dot y. The last one is up and to the right, so I'm going to add pixel dot x. I'm going to add pixel size dot y. If we want to be consistent with this image here, then we can change these down here to plus equals. Let's do the other column now. It's going to be bottom left. That's minus on the x, as well as a minus on the y. Down below, no transformation on x. New pixel size dot y. Down 1 on the y. Then, of course, our last one, positive x, negative y. It's already set up. And to be consistent, these are negative. Let's change these to negative. And that's it. There is our vertical Sobel filter. The rest, of course, doesn't have to change. Now let's copy the horizontal one and we'll bring it over to the horizontal depth. So let's move this down. Horizontal depth. Depth is going to change a little bit. Remember that the depth texture is single channel. So we're not going to be reading RGB values. So our first change is going to be to convert all of these to simply reading the red channel. All of these texture calls here. Now, of course, we can't be setting a float equal to a vec3 here. So our sum value is going to simply be a float instead. If our sum value is a float, then we don't have to dot product it versus itself. That doesn't even make any sense. We can get rid of that, and we can directly check what the sum is. If the sum itself, as what single floating point value, is less than our threshold, then we'll return 1. It's not intense enough to be an edge. Our depth vertical is going to be very similar. It's going to have this floating point value instead. But of course, it's going to be on the vertical axis. So it's going to look like this. So let's have our minus on the x, plus on the y. No change on x, right? Doing this one here. Plus 1 on y, u pixel size dot y. The last one will be positive on the x, positive on the y. And if we're consistent, those are all positive contributions to the sum. These ones will be negative. And I'm going to have bottom left minus minus, then simply down 1 on the y-axis. So I'm going to subtract pixel size dot y. Then bottom right hand corner, plus on the x, minus on the y. Oh, these comments don't make any more sense, do they? I should change this to top row, and then this one would technically be the bottom row. You could change them for the ones up top, of course. So how is this going to look like in the main function, right? Well, we're going to have to accumulate these values somehow in order to find one final float representing whether or not there is an edge. So let's do them separately. Let's first compute the depth Sobel factor. We can call the Sobel depth horizontal function. In there, we can give it the depth map as the texture to read, and then simply our texture coordinate at our current pixel to read from. Then we can take the vertical depth, and it'll have the same parameter list, but it looks a lot neater. So, notice how we're multiplying them together. This means that if any of these two decide to return 0, it'll multiply the entire product to 0. So as long as one of the axes determines that there's enough contrast, we'll have an edge there, and that's good. Let's do our normal Sobel. It's going to be, I won't copy it. I'll be proactive this time. It's going to be our horizontal reading from our normal map and our texture coordinate. And then we're going to multiply it, of course, in the same way by the vertical with our, oh, I caught that this time. That should say normal map. I misspelled that. Then we'll take the vertical, add the texture coordinate, boom. So what are we going to do with this? Well, we're going to multiply the results together too. So our out edge is going to equal depth Sobel multiplied by normal Sobel. So if any one of these has returned 0 and has detected an edge, we will output an edge. So we can put this to use now. Let's load it into the framework. Let's make sure there were no typos and we don't have any compilation errors. Then we'll go ahead and put it to use. So we already set up the Sobel Pass shader program. Let's go into game.cpp and load that sucker in. So I'll copy paste the last shader and I'll change that to Sobel Pass. It's going to have the pass through because it's acting as a full screen quad. We are not passing geometry through this. Well, not meshes anyways. Then we're going to go and get our fragment shader from the Toon folder, sobel.frag. Let's run this and see if it made it through. No, looks like it stepped over. We're good to go. Of course, if we run the scene, it'll just load everything else. So let's go down to the draw loop. Right after we create the G buffer, we will have our normal map, our full screen normal map, and our full screen depth texture populated with information that we can use. So it's after this step and before we generate the scene itself that we want to generate the normal map. So let's add a new comment in there. Detect edges, right? Let's put everything to use. So our GL viewport will be the usual 0, 0, window width and window height. We're going to bind our Sobel Pass. Let's send it the relevant information. So it's going to have, going to have to set up the sampler 2D. So we're going to have a normal map. That one we can say is 0. Let's get our depth map bound to unit 1. The last thing we have to tell it is how big the pixels are. So we're going to send uniform u pixel size. We're going to send a vector 2 for this one as opposed to just a single float. It is a vector 2, of course. The x component is going to be 1.0 divided by window width. And then the y component is similarly divided by window height. We have to ask ourselves all the 3 questions, right? What are we rendering? Where are we rendering it to? How are we rendering it? We're going to be rendering it with the shader, but where are we rendering? We're rendering to our edge map. So we're going to want to bind that. Let's get these 2 textures in here. So GL bind texture. It's going to be a texture 2D. And we're going to get our normal map from our G buffer. And that's going to be from get color handle. If we go up to take a look at what we need, that's unit 1 is the normal map. So we can go back down here, get color handle 1. That's going to go to unit 0. I'm going to change the active texture unit to texture 1 so that we can bind our depth map. That's going to come from the G buffer as well. Bind texture GL texture 2D, and we're going to ask the G buffer for not a color texture but its single depth texture this time. After all that has been bound, we can draw our full screen quad, and then we can start unbinding these textures. GL bind texture, bind texture, GL texture 2D, GL none. Then we're going to want to unbind from unit 0, right? So it was still unit 1 when we called this. Now we're going to cascade back down to unit 0, and we're going to unbind that guy as well. Last two things to do, in reverse order, we're going to unbind our edge map, we're going to unbind our shader. And there we go. If we give this a run, I might as well do it in release. I set up release mode so I could do it faster in the videos. So we should see no change whatsoever in a regular run. Of course, we haven't put the edge map buffer to use, but let's peek. Let's take a peek, right? Let's see what Insight shows us. So you can see how it's really useful to have the G buffer, providing all the information we need to really quickly and efficiently Sobel filter the entire image as a post-process. That's really when the G buffer becomes useful, when you start putting it to use like that. Boom! There's our edges. We render our scene into our G buffer immediately afterwards. Our Sobel filter gets applied. It's all red because, again, it has, if you can see up here, the format is GL_R8, 8 bits for one red channel. So everywhere we wrote 1 is actually going to be represented on screen here as red. However, we have all these black edges, nice uniform black edge around the sphere, and all the planks are picking them up pretty nicely as well. And you can see the two textures being read into this are the depth map, which is actually really hard to see, but it's here. The depth map as well as the normals. So you could take a look here how the depth map would have had virtually the same values here from the plank versus the ground, since they're touching, and wouldn't have been able to detect an edge. However, since we do have our normal map helping us out, it's going to very clearly detect this edge. So let's see that, right? Before we move on, let's see what would have happened if we used only the depth map as our Sobel filter. So we'll comment out the normals, and we'll write only the depth map Sobel filter. You don't have to do this, of course. Let's just play around and see what happens here. If I go back to the normal map, oh, it's being a little laggy. Here we go. Oh, get out of the way. Oh, it actually did a terrible job of finding these. I wonder why that is. There is none here at all. Let's find the, let's take a look at this again. Yep, that's our depth map. Looks like the thresholds we chose are probably a little bit too high. It depends on the scale of the scene. I didn't realize until now. Let's lower that a little bit. Let's lower that to even more. Let's lower it to like 0.2. Depending on the scale of the scene, of course, the depth map may or may not find the contrast and values between depth that it needs to. Let's take another look here. Here we go. Now we're starting to pick up something with the depth map. We can see as it goes back against the skybox, there's a very definite change. We can add that in a little bit more even. Let's have 0.05 maybe. Let's see how that works out. Oops, I want to run with Insight. So the edges we were getting were purely based on the normals, which actually provided some pretty terrific results. But now we can see that our depth buffer is going to start contributing to all of this as well. So if we now multiply them together and bring back the normals, it should look mostly the same. This is again approaching on an area where it's really just up to you making the values work for your particular game, right? Not all of this code will just work if you one-to-one copy it to your projects. Let's see how it looks. Yeah, it still looks fine. So let's actually apply it to the scene, right? Let's see what it looks like if it's influencing the final image. Then we'll be able to really tell whether or not we need more help from the def buffer. So return everything here to normal if you've been changing it, but certainly do lower the thresholds for only the def map down a little bit. Now let's go to game.cpp. Or sorry, let's go to our deferred lighting shader, right? This is the one that puts the scene together reading from the G buffer. But now we have an additional texture to read from. Let's add a uniform sampler 2D U edge map. We're going to start using these edges in here as well. So if we see our get data location here, let's read from the edge map. Now again, it's simply full of floats. It's one channel, so we're going to grab a float. Edge factor, it's going to be equal to texture. Going to read from that edge map at the current texture coordinate corresponding with all the rest of the data. Going to read the red channel. And applying this is going to be extremely easy. Remember, this is going to be 0 when there is an edge. So we simply go to the bottom, we multiply edge factor by our final color contribution. And wherever there were edges, the scene will turn out black. So let's take a look. Oh, sorry, we have to actually still send this texture to the uniform, right? Let's go to game.cpp now. Just below detect edges where the scene is put together, we're going to have to add another texture here. So above the position map, we're going to have the edge map, and that's going to be at texture 4, or unit 4. It's our 5th texture. We're going to start having a lot of textures here. Let's move up to our active texture slot 4. So we're going to call texture 4 here as our active texture. Then we're going to bind texture from GL texture 2D, and we're going to grab our edge map color handle. It's a color texture, and it's the only one, so we're going to specify 0. We've added a new texture here, so we want to make sure to unbind it. So down here, I'm going to unbind, then I'm going to switch down to GL. Well, I can copy active texture 3 from here. Right, just keep track vertically of which one the current active texture is. We have 4, it gets bound, and then it gets unbound. So the next one to unbind is texture slot 3. So we set that one as active. We unbind it, then we move down to 2, unbind it, 1, unbind it. Now we're going through all of them. Now that it's being sent, we could run this guy and take a look at the scene. Cool. So we have outlines now. It's very, very noticeable on the sphere. Looks pretty cool. Once we rotate around to the brighter side of the shack, it'll be even more noticeable. But we do have these cool little outlines on the shack now. Could be made thicker if you would want to, but that's a challenge I'd like to leave to you as extra work if you wish to do it. As a little bit of an exercise, I should say. So what's the last step, right? Cell shading. In order to get that into the scene as well, we need to have a texture to help facilitate it, a step texture. If we look in our textures, I already have one here, and it's on Blackboard. Simply 4 bands of color. Let's load that texture in and let's start using it. So game.h, I'm going to load a new texture. Texture. Step texture. And adding this is very, very easy. Go to game.cpp. We don't need any new buffers or anything fancy like that for step textures, for cell shading. Let's go to this ground texture that's loaded here. Copy that block, and now let's load our step texture. That's going to be our assets, textures, step texture.png. So we're going to scroll down now. We're going to want to also expose this texture to the shader that is doing the lighting. So that's our deferred lighting shader here. Let's add that, and then we'll add it in the shader after. So we're going to have view step texture as our 6th texture now. And don't be surprised of all these textures we're sending to the shader. AAA games will use even more, much more than we're using here. So we have our step texture going in. That's going to be at handle 5. So we're going to need to add yet another one. GL active texture, GL texture 5. Hopefully this is becoming a little bit more natural to you now. Now we don't have to call bind texture ourselves. We have a texture object this time, so we can simply utilize its own bind function. Then we're going to have to unbind our 5th texture unit and switch to our 4th one. Unbind that, switch to the 3rd one, unbind that, 2nd one, unbind all the way back down. So now it's being sent to the shader, so let's go in there and let's set that up as well. So in deferred lighting, I'm going to add that extra uniform. Sampler 2D U step texture. So it's going to be fairly easy to implement. We're going to be using it as a function of the brightness of the light at this pixel. So we want the brightness, instead of being smooth, to be stepped. So let's take the normal dot the light direction, which is a function of how bright the light should be at this location. We'll use that to create a new variable called blocky, which, as you might assume, is supposed to be a blocky representation of what the color was. So we're going to take our texture, our U step texture. We're going to load it from the x-axis will be the intensity of the light, and the y-axis will simply be 0.5 on the texture. We're going to be reading the intensity, so we're just going to load the red component. So again, think about that. We're reading halfway across the texture from left to right. As the intensity of the light gets stronger, it's only when it crosses these boundaries that you actually will see a shift now. How we're going to apply this, so we're actually going to let the rest of the color apply itself normally. But what we're going to do is we're going to multiply not only by the edge factor, but also this blocky factor at the end here. If we run the program now, we'll have the desired effect. Or will we? Dun dun dun. We actually won't. So let's wait around until it gets to that sphere there. And we'll take a look at what the problem is. It seems to be working if you peek at it from over here. But something will be slightly wrong. So it seems to be kind of following a little bit of a step. In fact, you can kind of identify where the lines are, but it definitely doesn't look anything like what we saw in the lecture. These edges are still a little bit smooth. They're kind of acting like a gradient. That's not what we want. Remember how hard the edges we're actually expecting to be like. If we look at our image here, we should be seeing something like this, nice crisp lines. The reason we're not is because the step texture right now is actually being smoothed. Remember, we have by default on all our textures linear interpolation enabled. So because the texture is so small, sampling around this area is actually going to slightly start interpolating versus the brighter colors. And these edges will be smoothed out, which is exactly the opposite of what we want. So we need to add functionality in our texture class to disable this linear filtering here that we have hard-coded. So let's go into texture.h, add another simple little function, set what should we call it? Set filter, set nearest filter, because it's called GL nearest. So let's take this new function, let's bring it into texture.cpp. Gonna want to prefix that with our texture : class name. Let's copy this stuff over from here, from the load function. So we're gonna bind the texture in order to make it active so that we can change its settings. And we're gonna change its filter parameters, both magnification and minification, to GL nearest. So it's gonna get rid of mapping. It's going to simply take the nearest pixel. So if we go into our game.cpp now, we can call this function up here where we load our step texture. And the filtering will be forced to this coarse filter. I should say I should also unbind the texture after I make those changes, but let's see the results now. Oh, I could take a peek here, it's much more crisp. Yet there are a couple things left to talk about as soon as we spin around. So the texture filter is working now. Keep an eye out for these planks and see how they suddenly burst into brighter color as we come around. Here we go, they're kind of flashing. All of a sudden they brighten up. That looks kind of weird. Okay, these are crisp now, but if once we get closer, you'll see they're kind of a little jaggedy. They're crisp, but they're a little bit rough. They seem to have some artifacts. Let's talk about the artifacts first. The artifacts on the sphere are caused by this buffer. The normals don't have enough precision in order to represent the smooth surface of the sphere. If you encounter an issue like this, one thing you can do is you can increase the bit depth of the texture. Of course, this will multiply the size of the texture, but if we change this RGB8 to RGB16, we effectively increase the accuracy of our normals. And if I run this again, let's also, before I run, unbind this texture, just to be consistent with the rest of the framework. Unbind after we make the changes. So if I run now, once we get back around to the sphere, you'll see that the lines are very crisp. But there's something else that we need to talk about too. We need to talk about aesthetics. Grab a seat. We have to have a talk. So this happens just about every year, where there'll be usually 2, sometimes 3 teams that want to tackle toon shading. But it doesn't really end up working too well. And the reason is you have to work with your artist to get toon shading to work. If we look at this scene honestly right now, and be honest to ourselves, it doesn't look all that great. Let me take a short detour and show you here that the lines are nice and crisp. Yeah, nice stuff. Back to depressing talk. So, if we're honest with ourselves, this scene doesn't really look all that terrific with toon shading. It's kind of cool, right? It's got a novelty factor to it. We wrote this, we just did this. But does it really add to the scene? Not really. It looks kind of weird. The ground texture is trying to be way too realistic to be trying to pull off this whole toon shading thing. The boulder too doesn't really look too great. These stripes don't fit in at all with the texture that it's using. The point here is, if you want to do toon shading, make sure that you work together as a team to figure out how the toon shading aesthetic can work well for your game. It's not just an effect to throw on for fun. It is relatively easy to implement, and it has terrific results, and it's used in AAA games, so I know it's really exciting. But just like everything else you do in your games, you have to think about it carefully, right? Does it fit the aesthetic? What does toon shading tell the user about my game, right? If you see a toon shaded game, somebody might assume that it's supposed to be some sort of comic book representation, maybe not so realistic, who knows? All of these have implications, and you should think about it, right? Don't just throw effects onto the scene just because. Unless, of course, you're in this graphics class and you want to learn about them, then of course throw them all on. But when you want to release and publish a game, really think about those things. So with that, I'd like to leave you. I hope you've learned something from the video. I'll see you guys next week. Have a good one. Hey, I'm back. I forgot to go through the files and show you top to bottom. But also I wanted to mention, I'm not singling anybody out with the Toon shading talk. Happens every year, and I was talking with Cameron Choden, and he realized as well that it happened every year, and he asked me to talk to you guys about it. So don't feel like I'm talking about you or anything like that. I'm just saying in general to be mindful about the effects that you throw onto your game. So let's take a look at the files. So texture.h, we can start here. Set nearest filter function added. Pretty straightforward coded here. If we go to our deferred lighting shader, the top, two new uniform samplers, edge factor, blocky, game.cpp, bit of stuff here, right? New edge map initialization at the top. Sobel pass was loaded in. No changes down here. All the good old stuff. Go to game.h. We have nothing new up here, but we have some new data members. And of course, good old Sobel. So, thanks for watching, guys. See you next week.